All right, this is Mr. McCord's ICP class, Unit 5, Assignment 3. We're looking at polyatomic ions today. So the other day I was looking at stuff at the store and I found this stuff, Epsom salt, that you can get for soaking. If you got sprains, bruises, you put it in a tub with some hot water. Apparently it's a laxative. You need that. Or if you need to supplement your plants, it's kind of a multifaceted product you can pick up. Now, based on what the label has told me, this is made up of an ionic compound involving magnesium and sulfur and oxygen. So I went and looked it up. And this is the formula for the ionic compound. So it's 1 Mg ion and 1 S ion and 4 O ions, apparently. But with what we've been talking about, I tried to put this together, and it didn't really work out. So the way that we would expect, we go find these on the periodic table. Magnesium is in the second column. It's got a positive 2 charge as an ion as it loses its 2 valence electrons. Sulfur and oxygen are both in the 16th column, and they like to gain 2 valence electrons, so they should have a charge of -2. Well, this is a little weird, because magnesium alone does not have nearly enough electrons to kind of go around for all these oxygens and this sulfur ion. So that's a problem. We also don't have nearly enough positive charge to cancel out with all this negative charge. So that also doesn't really make sense. It's kind of like we've got way too much negative all piling up on this little itty-bitty positive charge that can't keep up. So something about this isn't working. This isn't really what this MgSO4 compound is structured like. So that will not do. Okay. The thing is, sometimes ionic compounds include ions that are not just a single atom. So jumping to conclusions, we could say that, if I've got MgSO4, every one of these is its own ion that I can pick directly off the periodic table. But sometimes we have ions that are made of multiple ions. Okay? We call those polyatomic ions because poly means many and atomic means atoms and ion means charged atoms, ions. So a polyatomic ion just means we've got a couple atoms stuck together, and all together they make up a single ion with a single charge, like a -1 or a -2 or a +1 or a +3, something like that. So if I do a little bit more digging, I can find out that this MgSO4 actually has a polyatomic ion in it. And it's this whole SO4 thing. SO4 is a polyatomic ion called sulfate. Okay? Altogether, this SO4 has a -2 charge. We said before that magnesium has a +2 charge. Okay, well that looks a little better. Maybe this is going to work out. A +2 charge and a -2 charge should cancel out. That's totally feasible. Okay, so the way that this sulfate polyatomic ion looks and sticks together is a little bit more complicated than we need to get into right now. So for now, all we need to worry about is this SO4 we call sulfate is a polyatomic ion. Okay, that is just some atoms stuck together, and we treat them as a single ion. So we treat this SO4 as if it was one thing we would find on the periodic table with a -2 charge. All right? I don't split this guy up. I don't try to count out electrons, individually. This is one thing, and I leave it like that. Okay? I could have a couple of these if I needed to, but I always keep that ratio the same, where I've got 1 S and 4 O's. Now, recognizing a polyatomic ion in an ionic compound can be very hard. Okay, so to make it a little bit easier, we're going to put parentheses around a polyatomic ion whenever it shows up. Okay, that way you can recognize it as a group of atoms that all together have a single charge, like a -1 or a -3 or a +2 or whatever. If you ever see a piece of an ionic compound that has parentheses around it, that's going to be the way I'm indicating that that's a polyatomic ion. Okay, and to figure out what kind of charge it is going to have in an ionic compound, we look at this list of polyatomic ions. For this class, you don't have to memorize any of these. The list will always be available, and you should go to it to figure out what you're dealing with. It'll also tell you what we name that polyatomic ion to keep it from kind of getting confused with stuff we would always find on the periodic table as it is. So if I'm dealing with something like this MgSO4, I don't want it to be called magnesium sulfide oxide or something like that. I want it to be called magnesium sulfate to distinguish it from other compounds that might involve those elements. So the polyatomic ion is a specific arrangement of those different elements in that ratio. Now, trying to figure out the structure of this is actually really hard. As we kind of see here with this example, this doesn't work out too well, okay? But this SO4 thing also can't be ionically bonded together because these guys would make negative ions, kind of like what we had here. So we're not really going to worry about drawing this out. This involves a type of bonding we haven't covered yet, okay? All we're going to worry about with ionic compounds that contain polyatomic ions is the name of that compound and the formula of that compound. And we're going to be able to bounce between the two of them. Okay? So if I say that we are making a compound that involves one element and one polyatomic ion, so like maybe sodium is our element, and we are trying to combine it with the polyatomic ion nitrate, then we've got to put those together in some way that cancels the charge correctly, and we use that to figure out the formula. So we're going to kind of skip the drawing part of this. Now before, we figured out the formula a lot of times by making the structure and then counting up what we've got. So if I didn't have this and I just said I want a compound with magnesium and the polyatomic ion sulfate, but I can't draw out this, I can figure out what this formula is with a little shortcut we call the ion crossover method. Okay? We're going to basically use the charges that should cancel out in the ionic compound and switch them over to figure out what the formula is going to be. We're going to demonstrate the ion crossover method with some regular ionic compounds first before we make it a little bit tougher with polyatomic ions. So here we're making ionic compounds out of these pairings of elements, sodium and chlorine, NaCl, magnesium and chlorine, so got Mg in there instead, magnesium and phosphorus, switching out for a P, and magnesium and sulfur, so I'm switching out for an S. All right? With regular elements, we just look on the periodic table to figure out what their charge will be. In this case, again, we're going to skip the whole structure part, which means we don't need to look at valence electrons. We're going straight to charge, okay? It should be a shortcut up at the top of your column, just like valence electrons would be. So, for instance, our sodium is in the first column. It should have a charge of +1. All right. Chlorine is in column 17, the halogens, and it should have a charge of -1. All right. Chlorine shows up again here, so I'm just going to write that out. All right. Magnesium is showing up a bunch of times, so we can go find it in the second column. Magnesium has a charge of +2. Okay, phosphorus is in the 15th column in the nitrogen group, and it has a charge of -3. And sulfur is in column 16. It's in the oxygen group with a charge of -2. Okay, so rather than trying to swap around valence electrons to get everything happy, the shortcut I can take here is that all my charge should cancel out in a happy ionic compound, in something that is more stable. So any positives should cancel out with negatives. I should have an overall charge for the compound of 0, zilch, nada. So the shortest way to do this is to cross over the charges that I have here to see what my little numbers down here are going to be, my subscripts. So whatever the number of the charge is going to be, that's going to become the subscript of the other ion. So my 1 here is going to cross over down to the bottom of Cl and wind up right there. And the Cl's -1, I'm just taking the 1, no negative, is going down to the bottom here by the Na. So I'm taking the numbers from the charges and switching them over to the other ion. Okay? So we leave behind any pluses or minuses that come from the charge because we can't really have a negative number of NAs floating around. It's going to be 0 or it's going to be some positive number. So we drop all the pluses, we drop all the minuses. We're only taking the number part of it and switching it over. So the formula of this compound is just going to be Na1Cl1. Okay? The 1 kind of is implied. I wouldn't write Na if it wasn't there at least once. So I can get rid of 1 subscripts and kind of leave them out. So this is the way we would probably find this ionic compound's formula, NaCl. Okay, let's try the next one. Magnesium's charge of +2 is going to cross over. I'm just going to take only the 2, cross it over, so it's going to be next to the Cl. And the Cl's -1 is going to have its number, the 1, cross over to the magnesium, right there. So our formula for magnesium and chlorine coming together as an ionic compound is just going to be Mg1Cl2. Okay, again, the 1 is kind of implied, so we don't need it. So our formula can be cut down to just MgCl2. Again, no need to go through the structure or trade around valence electrons, no give and take. We're just crossing over these numbers here. Makes it a lot quicker. Okay, this one would usually be very nasty to figure out because we got 2 things that don't really trade electrons easily. We'd have to give up, 2, and then that wouldn't be enough for this phosphorus. And we have to go again and again. This usually takes a long time if you're trying to figure out the structure of this. But if we do the crossover method, I'm crossing over magnesium's 2, and this 3 from phosphorus's -3 charge. Okay. Again, I don't cross over a -3, just a regular 3. So I'm going to get Mg3 P2. As simple as that. And that's my formula. You can even go back and check and make sure that amount of charge will cancel out. If I have 3 magnesiums with a +2 charge, that's +2, +2, +2, that's a +6 charge overall. Okay? My phosphorus has a -3 charge, and I have 2 of them. So that's going to be -3, -3, that's a -6 charge. So altogether, +6 charge and -6 charge will cancel out to 0. This is a neutral ionic compound and is ready to go. It is a good compound to make. Okay? Now, there's one kind of thing you have to watch out for that I'm going to show you with this last one here. Okay? Let's cross these over, just like we did before. Where my 2 is going to come down here. And my 2 for my sulfur is going to come down here. Okay. Well, that means my formula for this compound is going to be Mg2 S2. But we've looked at compounds like this before, and we haven't needed to have 2 of each of them. If we look at the charges, an Mg2 plus and an S2 minus, a +2 and a -2 should cancel with just 1 of each of them. So we don't really need to have 2 of each of them. So if you see a compound with a formula like this, where you can kind of reduce it down divide all your subscripts by something to kind of get them down to a lower number, then we should do that. Okay? A lot of times with these kind of problems, you will see it when it is the same thing. So like a 2 and a 2, or a 3 and a 3, or a 4 and a 4. So we just reduce it down. So if you have a 2 and a 2, it's just going to become a 1 and a 1. So this would be Mg1S1. But again, we don't really need to show the 1, so it would just be MgS. Okay. That's the ion crossover method. And it's going to make it a lot easier for us to figure out what an ionic compound is made of, to figure out the formula.